All right, we're back, and today we're going to talk about electric fields. Last video, we talked about electric forces. And the idea of the electric field is a model because, in classical mechanics, besides gravity, when we usually think of forces being transferred, usually the objects have to be touching in some way. And so this idea of charges that are applying forces on each other at a distance is a bit outside of the box. It's a bit different than what classical mechanics was used to at the time. Of course, the same issue arose with Newton's universal gravitational law, and his answer to it was a gravitational field. And the answer to the force at a distance for charges is going to be the electric force. All right. And so the electric field, essentially for forces to be felt at a distance, there must be a field that's going to telegraph the force, something to announce the force to the other charge. And I need to make this very clear is that this is a model. So when you hear about field lines, don't take that too seriously. It's a good model, but I wouldn't necessarily say that it holds any truth to it. What's the saying is that a model can be useful even if it's not true. So this is a model we use for thinking about the electric field. And field lines emanate radially outward from positive charges. So as you can see, I've got a picture over here with a positive charge. And we have these electric field lines drawn in red that are pointing away from it. At all points, they're pointing radially outwards. And then as you can see for a negative charge, the field lines point radially inwards. So you can see my drawing down here of these. This is a negative charge and the electric field lines are pointing into it. And one term for this is you could call the positive charge a source, right? A source, because it looks like the electric field is flowing out of it. And you might hear the negative charge be referred to as a sink in a more general sense. So a sink, like there's a drain there. The electric fields are terminating at the negative charges and they're emanating at the positive charges. All right, so how do we calculate it? Well, the electric field, which is a vector, by the way, can be calculated by taking the Coulomb constant, timesing it by the charge that's creating the field, and then dividing by the distance, the shortest distance between wherever that charge is and wherever you're wanting to measure the field at. And so it really is important, because as you could probably guess, around this positive charge, the electric field is the same at any given radius because the electric field strength is based on the radius, right? So as I go further and further away from the charge, the electric field is going to decrease, but still point radially outwards. So where you want to measure the electric field at is very important. And of course, there's the other way to calculate it, which is the electric field equals Q divided by 4 pi epsilon sub naught times r squared. Once again, both of these are in the r hat direction. You may notice I didn't put the magnitude sign in on the charges. And the reason for that is for the electric field, it kind of makes sense not to. Because the r hat vector always points radially outwards from your charge. So here's a radial hat vector. And so if our charge is negative, right? So if positive r hat's this way, and we plug in a negative charge, all of a sudden it's pointing radially inwards, which is exactly what we want. So in this case, I'm just going to go ahead and leave it as is. Of course, just know that the fields always point away from positive charges and point into negative charges. So I have a very similar problem to the Coulomb force problem here. This time there's only one charge though, Q1, and we're going to try to figure out what the electric field strength is here at this point. And so in order to do that, we can go ahead and plug in K sub E, the Coulomb constant, times it by the charge, which is positive in this case. and then divide it by the radius squared. Conveniently, the radius is 1 meter, makes my life easier. All right, and then, all right, so the electric field strength here at that particular point is, of course, in the r hat direction, is going to be 8,990. And the units for the electric field at this point in the game is going to be newtons per coulomb. You'll see why in a minute. And it's in the r hat direction. So if we were to draw this, the electric field vector at this point, it would be pointing radially away from the charge, and it would have a magnitude of 8,990 newtons per coulomb. Now, dimensionally, we may look at this and say, okay, so the electric field is newtons per coulomb. Let's think about what that means dimensionally. So what that means is that if I put a 1 coulomb batch of charge at this point, so imagine I'm going to take a particle with 1 coulomb charge and I place it right where this asterisk is, that's going to feel a force of 8,990 newtons. Okay. All right, so now let's look at kind of one of the shortcuts that'll be important to know. So let's say you have a test problem that asks you to calculate the electric field caused by a certain charge at a certain point. Okay, so you do that just like we've done here. Then the next question says, now place a particle of this charge at the point you've calculated the electric field at and figure out what the force on that charge is. All right. So you might think force and then immediately go to Coulomb's force law, which will give you the right answer. Nothing wrong with it. But it might be a little bit of extra work. So here's what you could do. Another way to go about it is to notice that, okay, so when we calculated the E field at this asterisk caused by charge 1, we plugged in Ke times charge 1 divided by r squared. Well, you may notice that the only difference between the electric field calculation, well, one of the only main differences between the electric field calculation and the electric force calculation is the electric field calculation has the absence of the second charge. Okay, so over here with the electric force, we have this extra charge, and for the electric field, we have nothing, because the electric field is the field that the charge 1 is creating, but we don't have a charge 2 in the picture yet. So now if I go ahead and drop charge 2 in here, and for fun, we'll make it the same problem as the last video. So this charge will be 2 times 10 to the minus 6 coulombs. Well, now all I have to do to find the electric force is I just need to, and actually what I'll call this the force that 1 is applying on 2, right? That charge 1 is applying on 2. All I have to do is take charge 2 and times it by the electric field that I've calculated for that point, for this point right here where charge 2 has been placed. And so the force that 1 applies on 2 is going to equal charge 2, which is 2 times 10 to the minus 6 times the electric field we calculated that was created by charge 1 at this point 1 meter away from it, which is 8,990. And of course, this is in the r hat direction because of, Q1 is a positive charge and Q2 is a positive charge. Now you'll notice if Q2 is a negative charge, that would flip this thing and they would be attracting. So that works well. So 8,990 times 2 times 10 to the minus 6, and we get the same result as the last video, about 0.018 newtons. And in this case, I'm just going to say it's in the r hat direction, or the radial direction, radially outwards from Q1. So yeah, another great equation that can save you some time. All right, so I hope this was helpful, starting to discuss electric fields. I know the model is a bit, I mean, it's a bit different, especially the field lines part. Like I said, though, just think about it as a means to an end. It's a tool so that our minds can kind of comprehend possibly what's going on. All right, so I'll see you next video where we'll be discussing more about electric fields.